So let me show you the relationship between electric current and magnetic field. I have here a power supply that's going to run a current through these wires. As we saw earlier, when we have a current, there's going to be a magnetic field that forms around this wire. Now, the magnetic field around one wire is not very strong. That is why I have here a solenoid. Solenoid is just one wire that is looped over and over and over and over. Each loop is going to generate a magnetic field, and the total magnetic field, when it's all added together, it's going to be quite strong. This magnetic field is going to be directed this way, so it's going to come out of this end. Basically, this is going to be our north pole of our magnet. The magnetic field will loop around to the south end of our magnet. Now, all I have to do is apply a current to the coil, and I've got myself the magnet. To show you that it is magnetic, I have an actual magnet, a permanent magnet. And if I stick it inside so that the north pole of this magnet matches the north pole of this magnet, then it should repel. So let me turn on my power supply and watch what happens to the magnet. 3, 2, 1. It just shoots out the magnet. And if I flip it around, instead of repelling, it should attract. And just pulled it right in. And so we see that there is indeed a magnetic field that forms due to a current, and we've got ourselves a beautiful device, an electromagnet that we use in all sorts of equipment. Just as a current can induce a magnetic field, we also have a situation where a magnetic field can also induce a current. This has to do with relative motion between magnetic fields and conductors. Whenever you have a changing magnetic field near the conductor, it is going to induce a current and thus a voltage in that wire. The strength of the voltage is going to depend on the number of loops in the coil. It's also going to depend on the strength of the magnetic field. It also will depend on how quickly the magnetic field is changing. Just as a note, in order to induce a current and a voltage, you have to have a changing magnetic field. Just holding a magnet inside of a coil of wire will not induce a voltage. The magnetic field has to be changing, which is why in this figure you see on the left the magnet is moving downward, and on the right the magnet is moving upward. Also notice that the sign of the voltage changes. With the magnet moving downward, it gives you a voltage of +1, but on the right, with the magnet moving upward, it gives you a voltage of -1. So the magnitude of the voltage, the sign of the voltage, depends on the direction the magnet is moving. So the principle of electromagnetic induction says that when you have a coil of wire and you pass a magnet through it, it generates a current and a voltage from that current. So I have here, this box is a voltmeter. It's going to measure the voltage of this coil. I'll go ahead and turn it on. So you can see the number is pretty close to zero, pretty much zero, just a little bit of error. Now I have a permanent magnet, and I'm going to pass the magnet through this coil of wire. And as I do so, the voltage in my coil should increase. Ready? And you see that the numbers jumped up. Oh, in the negative direction. If I go the opposite direction, the numbers jump up in the positive direction. Negative, positive, negative, positive. So I'm creating a voltage and thus an electric current through this coil. This is how we generate electricity in normal everyday power production facilities. You have some way of having a coil of wire and changing the magnetic field back and forth through time. We saw one generator where we have a magnet passing through a coil of wire. Traditional generators actually have a wire that is turning inside of a fixed magnetic field. Either way, we are changing the magnetic field that is flowing through the loop. So the way that a typical generator is constructed is you have an axle that has the wire loop on that, and then the wires are connected to leads, which will alternate as positive and negative polarity. If they alternate, then your current is also going to alternate along with that voltage. So we call that an alternating current or an AC generator. And that's what we see in the top figure in this slide. Now, there are ways that you can hook this up so that when you have this loop of wire that's turning within a magnetic field, you're going to maintain positive charge on one of the leads and negative charge on the other lead, which means you have a relatively consistent current. Your current is always flowing in the same direction. So we would call this a direct current or DC generator. So you're always going to have either a positive or a negative voltage. It's never going to flip back and forth like we would with the AC generator. There's another really interesting and very useful property that we can make use of with this inducing currents, electromagnetic currents. It's what we call a transformer. Imagine you have a circular piece of iron, and on one side you have, say, 10 loops of wire, and on the right side you have one loop of wire. On the left, the 10 loops of wire are what we call a primary coil, and on the right is a secondary coil. The primary coil on the left, by the way, this is what you're seeing in the top left figure here on the slide. The primary coil is under a voltage of, say, 120 volts. Now, remember that when you have an alternating current, your magnetic field is going to be changing and alternating with the current. And when you have a changing magnetic field going through the secondary coil, that's going to induce a voltage in that secondary coil. Now, how much voltage will be in that secondary coil? Remember, that depends on one of the functions that determines the strength of the voltage is the number of coils. So in the secondary coil, if you have fewer coils, then you're going to have a smaller voltage. So in this example, you have 120 volts in your primary coil with 10 coils in it, but your secondary coil has only one turn, so it's going to be 1/10 of the initial voltage. So you drop the voltage from 120 volts to 12 volts. Now, the picture in the upper right of this slide is a picture of a typical transformer you would see out in a city on the power grid, where you have one current going in and it changes the voltage from a high voltage to a low voltage, or if you look in the bottom left figure, you could go from a primary coil that's smaller to a secondary coil that's larger, so you'd go from a smaller voltage to a larger voltage. The relationship is set by this equation. It comes from the relationship that the amount of power in the primary coil has to equal the power in the secondary coil. The power does not change. It's only the number of coils that changes. And so this equation comes out of that relationship that the power in is equal to the power out. Says that the voltage in the primary coil divided by the number of turns in the primary coil has to equal the voltage in the secondary coil divided by the number of turns in the secondary coil. And this principle is very useful, helps us to actually very successfully transmit energy from the generator, from the power plant, all the way through miles and miles and miles of transmission to your own home. And the way we do that is we increase the voltage very, very high so that we have very small power loss to a lower voltage that you can use in your own electrical outlets.